Hi everyone, today's presentation is hybrid Droop-Based control for parallel operation of DC-DC converters in a DC microgrid. This video is recorded for CPSPEG annual meeting in 2025. My name is Naser Souri. I joined Virginia Tech in 2022 working in Regal Lab, and my focus is modeling, control, and the stability of AC and DC microgrids, plus converter modeling and control. This slide shows the content, which is introduction. I'll give you a brief introduction, then the challenges of DC microgrid, power sharing issue, circulating current issue, and then I'll propose my hybrid droop control method, and then I'll give you the design of the controller, the communication delay and compensation, and the simulation result and experimental result. DC microgrids enable the integration of DC sources, and it requires fewer power conversion steps than AC grids, which reduces the losses in the system. Furthermore, due to the growth of DC loads such as servers in data centers, DC power is gaining more attention. Despite the advantages, they also come with some challenges such as fault protection. DC faults can result in very high and rapid fault current rising compared to AC fault. There are difficulties in detecting fault location due to the absence of frequency, phase, and zero crossing information. Another challenge is cybersecurity. Distributed energy resources need communication, which make it vulnerable to cyber attacks. Another challenge is control. Voltage regulation at DC bus, power sharing between converters, and stability issues such as local oscillation due to the interaction of the parallel converters, managing transient responses to load changes and disturbances, and ensuring a fast dynamic response are control challenges that require a proper design of the controller. Power sharing issue arises when there is a mismatch between the converters or cables that connect the converters to the load bus. Any difference in the size or length of the cables causing the converters to have different VI characteristics, as you can see in the figure at the bottom, figure A. Then different VI characteristics makes the system to deviate from its nominal operation point. Furthermore, any difference in the voltage at the converter's terminal creates a circulating current between the converters. As you may know, droop control is utilized to address these challenges. However, conventional and nonlinear methods are not flexible enough to adapt the grid changes. Therefore, adaptive methods or a combination of the methods can address the issue. Let's discuss more about circulating current. This current does not contribute to actual load and circulates between the converters. Therefore, it increases the power loss. As shown in the figure at the top, using the two-port network, the converter's current is obtained. The second part of these equations is the circulating current. If we write the power loss in the cables, then we can see unequal loss distribution on these cables, which leads to thermal stress on the cables. This figure shows the ratio of the circulating current to the load current on the y-axis, and it shows the ratio of the converter's current on the x-axis. When this ratio is 1.5, then 20% of the load current circulates between the converters. Our proposed method for power sharing is hybrid droop control. This method proposes the use of a constant droop gain plus a droop voltage corrector to compensate for the conventional droop control. This equation shows the modified voltage reference, and the control block diagram shows the detail. VR is the conventional droop control, VD is the advanced droop control, and VB1 is the voltage from the secondary layer, and LF, which is the load factor, it shows the ratio of the current of the converter, which is in this case there are two converters, which is K1 over K2. An adaptive integral controller is used to create a corrector voltage. This controller has scheduled gains to improve the performance. The figure at the bottom shows the frequency response of the design closed loop. The overall controller has a 90-degree phase margin, ensuring stability of the converter. After design, the controller stability analysis is performed to track the poles with change of cable resistances and other parameters such as delay. The closed loop transfer function is obtained using these equations, which depends on the controller design and grid parameters. The figure at the top shows the pole variation with changes in Kp and Ki in the control loop. As they increase, the poles move toward the imaginary axis. The third figure shows the pole variation with change of the resistance of the cables. And the last figure shows the pole locations when the communication delay increases. Communication is crucial in a microgrid, enabling coordination, control, and power management of distributed sources. However, a delay introduces phase lag into the system, leading to oscillation. To compensate for the phase lag, a lead lag compensator is proposed. This compensator enhances the performance. The figure at the bottom shows the general control block diagram of the system that is used to validate the proposed method using two DC-DC converters in parallel. This slide shows the simulation results. The simulations are performed in MATLAB Simulink for two buck DC-DC converter, and this slide shows two case studies. The first one is power sharing activation. This case study shows the power sharing before and after activation of the proposed method. And the other case study shows the proportional power sharing and load changes. At t equals to zero point 0.2, proportional power sharing is applied to the converter. And as you can see, they follow the references, the power sharing, proportional power sharing references. And then at t equals zero point 0.7, a load change is applied to the system, and they share proportional power sharing. This slide shows the impact of communication delay. Using the proposed method and lead lag compensator, the settling time is reduced by 40% and overshoot is reduced by 2.5%. This figure shows for 50 millisecond delay in the system. And for 100 and 200 milliseconds, these two figures shows the performance of the current sharing. Experimental results are performed to validate the method, and this figure shows the testbed of the parallel converters that I built in our lab. Uh, So these are the results for experimental result. The same case studies are performed here as simulation. The first case study is power sharing activation, and the second one is proportional power sharing and load sharing, which also, as you can see, the bus voltage is regulated at 48 voltage, regardless of the changes in the current. This figure shows another result for power sharing, and the first case study evaluated the effectiveness of the proposed method in response to constant power load, and the second one shows constant power load step changes. In both cases, the DC bus voltage is regulated at 48 voltage uh, volt, and then the current follows the power sharing or equal power sharing or proportional power sharing. Therefore, a hybrid loop control is proposed for power sharing by adjusting the reference voltage in the control system. It ensures a fast response and even with communication delay in the system. This method achieves average zero error in the current after power sharing is activated, and the phase compensator reduces the settling time by 40% compared with no compensator in the controller. Plus, the current overshoot is reduced using the phase compensator by at least 2.5%. Thank you so much for your attention.